They can taste the different colors of Skittles. We wanted to conduct an experiment to perform a significance test to see if students can really taste the rainbow. So there's 150 Skittles in the experiment, and they were able to identify 97. All right, so if we use our values, so 97 were correct. How many total? 150. That together is going to give us our statistic, our p-hat, which is 0.65. Okie doke. Now, let's go back and we're going to revisit the state, plan, do, conclude steps, right, that we use with our intervals. We're going to keep using those on every test we do. So that stays the same, conditions stay the same, a lot of things get repetitive. That's kind of nice. All right, so parameter, we want to define what it is we want. P equals what? The true proportion of correct guesses of Skittles. The true proportion of correct guesses of Skittles. All right. Now, significance level is given to us at 0.05. So the null and the alternative. Now we're using P's, right, for proportion. Now the value we're going to use here. All right, let's stop and think. How many colors of Skittles are there? 5. So if you had no taste and you were purely guessing, what's the chance that you get it right? 20%, right? So that's my null value here. 20% of you're just purely guessing. But what does our evidence tell us it may be? Greater than 0.2. So we're testing to see if that could be true. All right, now the procedure. Naming our procedure. We now have a 1 proportion z-test. 1 proportion z-test. We've done intervals and now a z-test, okay? Conditions. What are our 3 conditions? Random, 10%, and normal. Okay, was our sampling random based on the problem? Yes. Well, it didn't state it, does it? So we're going to assume random. It doesn't really state it. Not stated. Just making a note of that, unless I'm just missing it. Yep. All right, 10%. How many total Skittles? 150. Is that less than 10% of all Skittles? I think so. And then normal. How are we going to know if it's normal? Large counts test. So we take n times p, our p not value, the 0.2, right? So that would be 30. Greater than 10, and then we do 150 times 80, and that would be 120. Definitely greater than 10. It's a pretty random I'm sure the Skittles were random, right? All right, general formula versus specific. I'll show you the difference in a moment, but specific formula, if we're doing z-scores, we would do z equals p hat minus the p naught value over that standard error formula we've talked about before. So I'm going to show you the z-score method. You don't have to use it, but you need to be familiar with it at least. So if I plug in my values here, I get 0.65 minus 0.2 over 0.2 times 0.8 over 150. And let's just see what we get. Wow, we get a z-score of 13.68. How about that? Huh? It's pretty high z-score, isn't it? Are we okay? So if I draw the picture of the normal curve and I'm using z-scores, zeros down the center, 13's like way over here. .68, and we said it's a greater than, so I would be shading this little bitty piece, wouldn't I? So the test statistic is the 13.68. And the p-value using norm CDF, or you can use the test in your calculator. I'll show you that in a moment. Look, it comes out like this. Now, 7.32 e to the negative 43. What the heck does that mean?
It's crazy tiny.
Does that mean my answer is 7.32?
It's 1 decimal and then it's 42 zeros.
It's like 42 zeros after the decimal, and then 7.23, or 723, right? So can we say that my p-value then is approximately 0? Because think about it. In terms of probability, this is basically not going to happen, is it? Now, why do I bring this up? Because I have had students in the past that tell me a p-value in this case would be 7.32. So it can't be. Probability can't be greater than 1, right? So 7 should put up red flags in your head. No, it can't be. All right, so this is how you would write your answer in this regard. Okie dokie? Now, conclusion. Now we're putting together the decision stuff and the statements we made in section 1. So we're going to take that p-value we found. So since 0.00 is less than our alpha of 0.05, what do? If the p is low, we reject the null. And if we reject the null, so think about, here's our null, here's our alternative. If we rejected that, we found evidence for the alternative, didn't we? Okay, so we found convincing evidence. We have convincing evidence that the true proportion of correct guesses of Skittles is greater than 0.2. Is that okay? So remember, when we do this, what do we have evidence of or not evidence of? The alternative. Whatever the alternative hypothesis is what you put in here. No matter if we reject it or fail to reject. That's always what you're referencing. Okay? All right. Let's look at the back. This is just recapping that 4-step process we've seen a bajillion times now. Okay? We state the parameter in context, give the statistic, oops, can't see it, the hypothesis and the alpha. I'm going to name the procedure, and so the procedure right now is the 1 proportion z test, not z interval. We did those last time. So the plan step, we name the procedure and we check the conditions. Same 3 conditions we've been doing, random, 10%, and normal. The do step is where we show our work. You don't have to give the general formula or the specific, but you can. You definitely need to show your test statistic and p-value in a drawing. Okay? And then conclude is where we interpret our decision. Okay? So some people were asking, like, what is the general formula? Well, this is the general formula, and the reason we bring it up because this is the way it's shown on your formula chart. It's very, very generic, right? So standardized test statistic could be a z or a t. T is what we use for means. It could be z if it's proportion. So in this case, it's proportion. So this is the general. This is the specific for proportions, okay? Specific for proportions. And then you have your one-sided test, which is what we've done so far. It could be left, it could be right. And then we have a two-sided test. Now, as we've done all our tests, when we did like our one-sided test here, you mean our upper boundary would be whatever that z-score is, right? And then, I mean, the lower boundary would be whatever that z-score is, sorry. Upper boundary would be like positive 10,000, right? Well, how do you think this is going to work? How are we going to find the area when it's a two-tailed test?
Times 2.
Yeah, you're just going to find the area of one of the tails and multiply by 2. It's perfectly symmetrical. You just got to remember to multiply by 2. There is a shortcut to this, and I'll show it to you in a minute, okay? But if you're using Norm CDF, you have to remember to do that. Norm CDF won't do it for you. Okay, doke. All right, let's try this one. This next question. Sometimes parents and grandparents like to recount how difficult life was when they were kids, such as having to walk 10+ miles to school in the snow, uphill both ways. You know the deal. Random sample of 180 teenagers were selected, and 40% had heard stories from their parents and grandparents about how difficult life was when they were kids. Do the data provide convincing evidence at the 0.05 level that the proportion of all teens who have heard stories about how difficult life was differs from 0.5? So this is a differs from. It's going to be a two-tailed test. Do you see that? Did you catch that? All right. Now, parameter, here's our state step. What is P representing? Just use the phrasing, if you need to, from that sentence stem right above. Proportion of all teens who have heard stories I'm just going to say of difficulty. I'll leave it at that. Who've heard stories of difficulty. Okay? All right. Did they give us a statistic? It says a random sample of 180 teenagers were selected and 40% had heard the stories, right? Okay. Hypothesis. We know it's P. And this is P equals. And notice that right at the end of the thing it tells us it's 0.5, right? Differs from is going to translate to a not equals to 0.5. Alpha is 0.05. All given to us in the question. Okie dokie. Now, in the plan step, we're going to name the procedure. This is the one proportion z-test. And let's check our conditions. Was the sample random? Yes, it's stated N is 180. Let's check 10%. Is 180 less than 10% of all teens? I believe so. And now we check to see, is it normal? Well, we got to use what to do that? The large count test, and we use the null value, right? So we're going to do 180 times 0.5. What's that? 90. 180 times 0.5. That's 90. Both of them are greater than or equal to 10, so we're good to go. All right, so we've proven enough that the sampling distribution is going to be approximately normal. Okay, general formula, you don't have to worry about that. If you don't want to write it out, I get that. So let me switch over.